Hello, my name is Dr. Rebecca Bell and I'm a Senior Lecturer in Geology and Geophysics from Imperial College London. Today we're going to talk about plate tectonics. Plate tectonics is often described as the great unifying theory in the geosciences. Once you accept plate tectonics, lots of observations about the world around us suddenly make sense. It explains why we have mountains, why we have the deep ocean, and why we have earthquakes and volcanoes where we do. So plate tectonics says that the outer part of the Earth is divided up into a number of rigid plates. And those rigid plates are moving and interacting in different ways. We have divergent plate boundaries where plates are moving apart, and these are locations where new ocean crust forms, and that's happening very famously in the Atlantic Ocean at the Mid-Atlantic Ridge. In other places the plates are colliding together, and when that happens that gives us very large faults which can allow us to have very large earthquakes, like the 2011 Japan magnitude 9 earthquake that produced the devastating tsunami in 2011. In other places the plates are moving side by side, forming conservative plate boundaries and strike-slip faults, and probably the most famous example of that is the San Andreas Fault on the western coast of North America. And we're going to be talking about all these types of plate boundaries in this lecture. Those plates are not only made up of the crust, they're also made up of the upper part of the mantle, which is cooler than 1,300 degrees Celsius. And that part of the mantle behaves in a rigid way. So the crust and the upper mantle together form something which we call the lithosphere, and that's what the plates are made of. Those rigid lithospheric plates float on top of the hotter part of the mantle, which is called the asthenosphere, and that flows in a more ductile plastic way. A very common misconception that's still in lots of A-level textbooks is that the mantle is entirely molten, and that's not the case. The mantle is predominantly solid, but it can flow where it's hotter than 1,300 degrees Celsius, but very, very slowly. If the mantle really was molten everywhere, we'd have volcanoes popping up, in central London, which we simply don't see that. So the mantle only melts in very specific locations, and we're going to be talking about those over the course of this lecture. So these rigid plates have the same behavior as a biscuit. So if I take this biscuit and I snap it in half, if I was to imagine that each side of the biscuit is a tectonic plate, and I rub the plates together, you can see all of the crumbling and the cracking which is happening is at the boundary of those biscuits. The interior of the biscuit is staying relatively deformation free. And exactly the same happens with the tectonic plates of the Earth. The crumbling, the cracking, the development of fault lines, which is where we get earthquakes, and most volcanoes, all of those happen at the plate boundary. Sometimes that's called the plate margins. You might hear me kind of using those two terms interchangeably. The middle of the plate stays relatively deformation free. So the UK, where I'm speaking to you from at the moment, we are right now in the middle of one of these tectonic plates, which is why we don't experience many earthquakes. Firstly, though, it's useful to step back and have a bit of a history lesson and think about how the theory of plate tectonics evolved. And the person who's often coined as the grandfather of plate tectonics is Alfred Wegener, who was a meteorologist. In 1912, he put forward a radical new theory called continental drift. And his idea was that although the continents are, in the position they are at the current day, that wasn't where they've been throughout geological history. And in fact, he suggested that 250 million years ago, the continents were all grouped together as a supercontinent, which he called Pangea, and over time, they've all drifted into their current configuration. And he had several lines of evidence to propose that. Firstly, as any young child will tell you when they first look at a map of the world, some of the continents look like they could fit together like jigsaw puzzle pieces. The clearest example of that is South America and Africa. They just look like they can fit together really quite nicely. So that was one line of evidence. Another line of evidence was that fossil plant and animal distributions across multiple continents. You see exactly the same plant and animal species over very widely distributed continents. So it's impossible that those plants and animals can travel thousands of kilometers across the ocean to get from one continent to the other. It's also improbable that exactly the same species of plant or animal evolved on different continents. Alfred Wegener proposed that if you reconstruct the continents to form the supercontinent of Pangea, those plant and animal distributions nicely all line up together. So it really helps to explain those observations. Another line of evidence, which was very close to Alfred Wegener's heart as a meteorologist, was that 300 million years ago we have evidence of a glaciation in the Permo-Carboniferous. And evidence for this glaciation was found over very widely distributed continents. It was found on Antarctica, South America, Africa, Madagascar, India, Australia, places that are now very far away and at very different latitudes. And in particular for India, it's at the equator, so it's hard to imagine why a glaciation would, continue all the way from the South Pole right up to the equator in some places. Alfred Wegener also made the observation that when you have glaciations, they produce scratches in the rocks. And if you reconstruct the continents to form this landmass of Pangea, those striations form kind of radial patterns emanating away from that prehistoric South Pole position. So that's again all really good evidence that the continents were at one time together. So you might think that all of these lines of evidence, they're all quite compelling to suggest that the continents really do come together and drift apart. But Alfred Wegener was ridiculed when he put forward this idea in 1912 and really continued to be ridiculed right up until his death in 1930. One of the reasons for that is that he was very young when he proposed the theory in his early 30s. And as a meteorologist, he also wasn't a classically trained geologist. So the professionals at the time really kind of looked at him with some suspicion. But the killer thing Alfred Wegener couldn't do was to propose a hypothesis, a mechanism for why the continents could drift through the oceans. He couldn't come up with any, good mechanism why that could happen. So unfortunately, after his death in 1930, Alfred Wegener never got to see that eventually the scientific community did come to accept the theory of continental drift. In the 1950s, there were significant developments in our technology that allowed us to observe the Earth, largely as a result of World War II. We developed instruments that could allow us to very accurately determine the Earth's magnetic field and also enabled us to map the oceans. So in the 1950s, magnetometers were developed, which led to a new field of science called paleomagnetism, which is where scientists would go out and measure the magnetic field of rocks. As rocks form, the magnetic minerals within them which contain iron, such as magnetite, the magnetic dipoles will align themselves with the Earth's magnetic pole. What paleomagnetists found is that when they examined rocks of the same age across different continents, not only did the dipoles not necessarily point to Earth's magnetic North Pole, they all pointed in different directions. And as we only have one magnetic North Pole, the only explanation for that is that the continents have drifted and moved into new positions. So immediately once this observation was made, the scientific community had to accept Alfred Wegener's theory of continental drift. We've now got hard, quantitative evidence that the continents definitely moved. But that still doesn't move us closer to providing a mechanism. We didn't have to wait long until that mechanism came along. So in the 1950s, ships were going across the ocean, mapping the depth to the sea floor using sonar. So sonar involves sending out a high-frequency sound wave. That wave travels through the water. When it hits the seabed, it gets reflected. It basically echoes back. And we can detect how long it takes that sound pulse to be received. If we know the velocity of the speed of sound in water, which we do, it's 1,500 meters per second, we can use the simple equation, speed equals distance over time, that you'll all know from physics, to calculate the depth to the seabed. Prior to sonar, we had to measure the depth of the ocean, basically using a lead weight on a rope and dropping it over the side of the ship and then measuring the length of the rope, which gave us very accurate measurements, but it was very slow and very one-dimensional. With sonar, we can tow the sonar instrument at the back of a ship, steam across the Atlantic Ocean, for example, and collect two-dimensional profiles of what the seabed looked like. So when that was done in the 1950s, a very interesting discovery was made that in the center of the oceans, where you might expect the ocean floor to be at its deepest, it actually becomes quite shallow. And in the middle of all of the world's oceans, we have a mountain chain. And those mountains, in some cases, can be as high as 2 kilometers. And if we were to strip away all of the water in the oceans, they'd be the longest mountain chains anywhere on Earth, certainly longer than the Himalayas, for example. At the same time, people were making heat flow measurements across the oceans and finding that the greatest heat flow was coming out of where we had these mid-ocean ridges, these mid-ocean mountains. Magnetometers were also used offshore as well, so those instruments that can measure the magnetic field. And what they found is that in some parts of the ocean, the rocks that make up the oceanic crust, the oceanic sea floor, the magnetic minerals in them show a very high magnetic field. But in other areas though, the magnetic field measures much lower. And then you go to an area that measures higher again, and you end up with these stripes where the magnetic field has a different strength. And those stripes are exactly mirrored the other side of the mid-ocean ridges, those mid-ocean mountains. Paleomagnetists who were working on land at the same time had discovered that the Earth's magnetic field at certain times in history has reversed. So at some points in history, the Earth's magnetic North Pole is where it is today, but at other times, that magnetic North Pole actually goes to the geographic South Pole. So the effect that has is that when we measure rocks in the ocean, when the dipoles of the magnetic minerals are pointing north to the magnetic North Pole today, we see a high magnetic field strength. When they reverse and point to the south, at times when we've had a magnetic reversal, the magnetic field strength gets lower. So these stripes are actually showing us when the Earth's magnetic field has reversed. And because on land we can date the rocks where we've got those magnetic reversals, we've got a really nice way to date the ocean floor. And the fact those stripes are exactly mirrored either side of the mid-ocean ridges tells us that we've got crust of the same age either side of the ridge. So from those observations, it didn't take people very long to put them all together and realise that at these mid-ocean ridges, where we've got lots of heat flow, these are locations where the mantle is melting, it's erupting through the lithosphere, and we're having new ocean crust forming, which is giving us that high heat flow. At that mid-ocean ridge, we're getting divergence, we're having extension, the plates are moving apart, and that's causing the ocean crust, which was formed at one point in history, let's say when the magnetic North Pole was where it is today, that crust is being moved either side of the ridge. We might then have a reversal, new crust forms, with the dipoles pointing towards the South Pole, that the crust then gets moved away, and the process keeps happening, which gives us these stripes. So this led to the theory of seafloor spreading, and seafloor spreading gives us a mechanism for how the continents can move across the surface of the Earth. Because new ocean crust is being made at those ridges, that can allow the plates to move. One issue though is that if we're making new oceanic crust, that would suggest that the Earth's surface is actually getting bigger because we're making new crust, and the Earth isn't getting bigger, so we know that's not happening. Fortunately, there was an observation again made around the 1950s that helped to show what was happening. So as well as having these ridges in the middle of the oceans, in other parts of the oceans we had deep ocean trenches, areas where the seafloor is really deep. So the one you've heard of is probably the Marianas Trench. So at the Marianas Trench, that's a location where the oceanic lithosphere is actually being subducted. It's going down into the mantle. It's being recycled. So the theory of continental drift and seafloor spreading together led to the theory of plate tectonics. And this can be thought of as the world's largest recycling factory.